Joseph Wunderlich, Professor of Engineering, Architecture, and Computer Science. This is a review of Calculus 1 and 2, perhaps some in Calc 3 a little bit, of some things that you need to know before you look at neural network learning, deep learning, gradient descent learning. So if you have a function, f of x equals 2 to the x, the derivative is 2 because 2 to the x is x to the 1, and the way you do a derivative is you take the exponent, put it in the front, and then subtract 1 from the exponent. So the 1 comes down, it's still 2 to the x, x to the 1 minus 1 is x to the 0, and anything to the 0 is 1, so you just get a 2. Now, if you have two variables, f of x and y, and you're doing a partial derivative of x, partial derivative of f with respect to x, then you're going to just treat the y as a constant, so it looks just like the above 2x, except now the y is just like the 2, left with a partial derivative equals y. Then if you have something like this, 1/2 times 1 minus x squared, then that 1 minus x derivative of that is, the 2 comes down, and then in front of the 1 minus x, and then you're left with just to the power of 1 there. And then you have the derivative of what's in the parentheses, so that's what you see going on there. You see that -1 is derivative of what's in the parentheses. The next is doing it with partial derivatives and a function of x and y. And so in this case, the partial derivative of f with respect to x is just like above, where now the y is the 1. F of x equals 2, derivative of any constant is 0. F of x equals e to something is just, the derivative is just e, that same something, and then times the derivative of the exponent. Now, if f of x equals some fraction, x squared over 1 minus e to the x, then you want to break that into two pieces where you have an upper function and a lower function, u of x and v of x, and you use the quotient rule, v to u minus u to v over v squared, and then you just calculate each of the components there and plug it in. Now the chain rule says if I have a function y equals f of u, where u is a function of x, in this case g of x, then this is the way it looks. So the derivative of y with respect to x equals derivative of y with respect to u times derivative of u with respect to x. For example, y equals u squared. U is a polynomial and a function. And so you take the derivative of u squared with respect to, dy of respect to x is equal to dy with respect to u. So the derivative of u squared is 2u. Then the derivative of the polynomial is x minus 4 plus 0. So 0 drops off. And that's follow through with the rest of it. If you want the derivative dy of respect to x, y prime is another way of writing that. For this fraction, you consider the 1 as a function in this case. Or no, I take that back. You make the polynomial as a function. It's in the parentheses of is u. And then you have 1 over u cubed, which is same as 1 is u to the negative 3. So y equals u to the negative 3. And so that's a function, and you follow through and look at the derivative of that. Y equals x, the square root of x is the same as saying x equals 1/2. So the derivative of that, 1/2 minus 1 is -1/2 for the exponent. Put the 1/2 in the front, take derivatives, follows through the rest of it. Example 5, you have a choice here of the quotient rule on the left side, where there's a function, you consider x plus 2 a function in the numerator, and x to the 1/2 is a function in the denominator, and then you use the quotient rule. I might have said the chain rule. Use the quotient rule there. On the right side, you just simplify it out where you take the denominator with two parts of the numerator and then expand it out, and so you get y in different form. That you don't need the quotient rule if you do that. Example 6, y equals 1 over x. Well, you could use the quotient rule there if you want. Treat 1 as a function in the numerator and x as a function of the denominator, and then you do the work you see there. Or simpler, just say that, oh, well, y equals 1 over x is the same as y equals x to the negative 1, and then that's just a simpler way of doing it. So we did the regular chain rule above, the dy with respect to x. Now we're looking at a little more complicated thing where we have a function z is a function of x and y, where both of those are a function, the x and y are both a function of another variable t. And so it's a little more complicated here. And you see partial derivatives mixed with regular derivatives here. So derivative of z with respect to t is equal to the partial of z with respect to x times the derivative of x with respect to t times the partial of z with respect to y times the derivative of y with respect to t. So for example, z equals x squared plus y squared, where x equals sine t and y equals e to the t. So you calculate it out as it shows above, knowing that the derivative of sine is cosine, and you know how to do the derivative of e to x. And they just show that you could move things around and maybe do it a little simpler. Now we have another case here, example 2, or theorem 21.4, where f equals, or z equals a function of x and y, and now y is a function of x. So the two variables nested inside there are a function of each other. And so then you get the derivatives of this z function with respect to x equals the partial z with respect to x plus the partial z with respect to y times the derivative of y with respect to x. So as an example of that, you can look at that. Now, if we have another kind of thing here, we have z is a function of x and y, and x equals a function of two other variables, u, or another, x is a function of u and v, and y is a function of another variable g, or another function g of u and v. So we got a bunch of complexity here, and so multivariable chain rules expanding here to look like this. And so example 3, if I have z equals x cubed minus y cubed, and x equals u plus v, and y equals u minus v, then you see all that you need to do there. Whether you're looking for the partial z with respect to u or the partial z with respect to v. Two different things that you may need. So do that. Here's a problem that's not just symbolic, but you have numbers to plug in. So we want to find the rate of change of a volume at a given time. And we know at that time that there's certain measurements of this cylinder that's changing both its radius and its height. We're given those, that it's changing at a constant rate. The radius is changing at 2 inches per minute. It's increasing, and the height is decreasing while the radius is increasing. The height is decreasing at 4 inches per minute. And so we want to figure out the rate of change of the volume at a certain point in time when the dimensions of this cylinder are radius 4 inches, height 10 inches. So we're going to use our chain rule. We know the equation for a volume. And so we're finding dv with respect to time, the rate of change of the volume with respect to time. So that's equal to the partial of the volume with respect to the radius. So we calculate that, holding the radius, or making the radius the variable. And then the height is a constant, so you see the answer there. And then the partial of the volume with respect to height. Now the height is a variable. and the radius is a constant. And now we have the other parts, which is dr dt and dh dt, which are those rates are the ones given to us that of the radius increasing 2 inches per minute and the height decreasing like 4 inches per minute. And so we plug those in, and then we have the equation down the bottom here, and it's all numeric, and you have a value. You have a numeric value. In addition to the calculus that we just looked at, we want to look at the method of least squares for finding the minimum sum squared error when we're calculating, we're trying to minimize the sum squared error to find optimal solutions when we're changing weights during the interconnection neuron weights when we're learning based on the training set. So to begin with, we want to just mention curve fitting here, which not only is important to the sum squared error, but also plays a part in how I came up with a all digital parallel processor single chip in 1992 by using polynomials to approximate the sigmoidal transfer function inside the neuron. But for here, we're just, this is just the beginning of curve fitting, or leading up to the method of least squares. So you can fit a curve to a line, or you can fit a polynomial to a curve during curve fitting. And so you see that there in that first graph. And then down in the middle here, you're curve fitting to a straight line. And the reason you're doing that is because if you have some points and then you notice that a straight line will fit right through them, then you're going to, your error between the points and the straight line will yield this sum squared error. So you see the equation of the line here, y equals mx plus b, or equals b plus mx, and there's the slope, b's the intercept. So you see that line. And so what we want to find is the minimum error here. And so using the equation of the line and the points, you have sum squared distances, and then you want to minimize that. And so you're looking at these conditions for that. And, without going through the derivation here, they take a look at it. The idea is to minimize the sum squared errors. And we'll see that in learning. And so you may want to come back to this, or it perhaps will be more clear when you see it in the context of the neural network learning.